Today's cranial gross anatomy, which I figure you guys already know, sort of, right? I mean, don't expect, I mean, I don't want to have to go through and say, this is a parietal bone and this is an occipital bone. You got that, right?
Yeah.
All right. Cranial arches. Oh no. Oh God, I can't put you through that again. I mean, I like them, but face development? Oh, well, we do the brain. Okay, we can do the brain. Not today, but brain's kind of fun. Well, it is a brain. So, I need, is it just us? Okay, it's always going to start at 3:30, guys. I'm sorry, but it's not my fault. I have another class that runs from 2:30 to 3:30, and then you have to run down here. So, apologies, but that's how it has to be. So, like always, I didn't try, but Connie upstairs tried to put my lecture on Canvas. Can you check? Is it on there? If not,
I did not see it earlier.
Are you looking for schedule or for,
is it on there?
it's from 3 to 4, it says.
Which lecture is it called?
Sorry.
It's cranial anatomy and facial development or something like that. Make sense?
No.
No, it does not make sense.
I mean, it makes sense. No, yeah, but it's not on there.
All right. Well, could somebody, one of you guys knows how to do this, right? You can load it and then give it to everybody.
Sure. Yeah, I can do that.
Libby, the note today for this class.
There are always those people that are really good at this stuff. And I am not. And you have to recognize your weaknesses. Which I have many, but that's one of them. And then you got to put it on the machine. Oh, I know, I'll turn that on. So how are classes going for you guys? Okay, now guys, I'm sure you know this, which is why I'm going to go through this. When you talk about the top of the head, you call it cranial or superior, right? All right. And when you talk about the bottom of it, it's inferior. But remember that when you talk about other animals, it isn't like that. It's cranial and caudal. So I just throw that out because you're aware of all that. And the front of the face is rostral. Rostrum, like a face, like in a dog. Oh, because you're going to bump into these terms. Proximal and distal, you got that too, right? Distal's far from your midline. Proximal's closer to your midline. So my hand is distal to my elbow, which is more proximal. And my shoulder is more proximal than my hand. So, and when you pull away from the midline, it's called abduction, abduction. Am I repeating? Do you know this? Just nod so I can say, okay, I can. I mean, you got to just know this. So that's abduction. A deduction is when you come towards the midline. Now that becomes important because when you talk about jaw muscles, they sometimes describe the masseter and the temporalis as being abductors. Maybe that's a bad choice of term, but they sometimes talk about adduction of the jaw, closing your jaw. You got mesium distal down in the teeth, buccolingual. You've got that, right? I hope so. Because if you don't, the world's in trouble. So okay, so just what we're gonna. So I'm not going to go over that in detail, and I'm not going to go over in detail the bones. Because do you all have skulls? Did they give? I know you have skulls, but did they give you a box with your own skull?
We can run them out. So we don't do them, but we can obtain.
Okay, because they should give you, each one of you should have your own box with a skull, but never mind, it's not my problem. But you should do that, because you gotta know the bones. So I'm not gonna point out this is a parietal, and this is an occipital, and this is an ethmoid, and this is a sphenoid. You all kind of get that, right? I hope, if you don't, I mean, we can go through it, but it's devastatingly boring to do so. It's just one of those things you just have to sit down and learn. Take an hour and just memorize the bones. So, having said that, oh, and I really do have, okay, at the end of this lecture, you're not going to get tested on it, but it is so cool. There's something I'm going to show you that is it is so cool. It's neural crest stuff. I just love neural crest stuff. I know, and you're going, oh God, not neural crest stuff. I know. All right, these are just, terms you should know for the test. That arrow, or that line through there, sort of breaks up what's called the viscerocranium or the splitocranium, which is your face, and the neurocranium.
What was the other name? Then visceral? It was visceral and.
What?
Where you said, you said.
Like, what was
Louder, I'm
that?
sorry.
Oh, sorry, viscerocranium, and you also call it a spline.
Oh, it's a viscerocranium, it's also called the splitocranium. And that's, it's all membranous bone except the, I think Hans probably told you this, the joint on the mandible, the condyle, which is endochondral. Did he tell you that?
Yes.
Okay, I think so. And what's the other bone in the skull that's not membranous? What's the occipital? The occipital is all endochondral.
Oh, yeah.
And the reason is the occipital was one time a vertebra that got moved into the skull so we have a neck. Because fishes don't have necks. So when you come out on land and you're a fish, and you start walking around on land, fish go like this, right? Well, meaning fishes don't have necks because their head is always going the direction. But in our case, when you come on land and you walk on land, if you didn't have a neck, you'd go like this. Well, you can't walk around like that. Come on, that's a bad way to walk around. So we stole a vertebra and made it into the occipital, so the occipital bone is endochondral. You're not going to get tested on this. Nobody is ever going to ask you that. But it's just, I find it to be a fascinating little fact. There's a chimp and a human. The whole point here is we've reduced our face enormously. We've really made it much, much shorter, and at the same time made our brain bigger, and that gives us this weird look. Every day we get up and look in the mirror and you think, well, that's sort of a normal looking face. No, it is not a normal looking face. If you were to ask a giraffe, do you think humans look normal? They would say, not on your life, you guys are weird. We have flat faces and big eyes and big giant heads, and we just don't look normal. That's another thing to show you the viscerocranium. All of which is neural crest. Keep that in mind. Yeah, I know, you guys have already seen this. We've been through branchiostoma before. Just remember that we are bilaterally symmetrical. We have a head end, we have a tail end, we have a right side, and we have a left side. And we have a notochord. So, and that's important to know because most of the animals on the planet don't have that. But mammals do. As I said, this is highlighting the viscerocranium. But just really quickly, that's the maxilla. It's made up of two pieces. And we're going to go through, once again, you remember when we talked about the prominences, how they grow together? If they don't grow together, you end up with a cleft. Well, yes. The maxilla, that's the maxilla, that's the zygomatic, that's the mandible. The human mandible is kind of weird because we fuse it here in the front, in what's called a mental process. But at any rate, I presume you probably know these bones. So, you know, the frontal bone, the parietals, the temporals, it's just, you guys have to just get an anatomy book and just sit down and memorize it. Also know the sutures. There's a coronal suture, and when they talk about a coronal section through a body, that it's called a coronal section from the coronal suture, which is to say it's coming through this direction. Also a sagittal suture. That means it's midline. It's going from front to back midline. Those are sagittal or parasagittal sections. That cute little. Yeah, we're going to talk about this later. I'm just going to really fast go through the human facial skeleton and what happened. First of all, we moved our orbits to the front. You and I, we all have binocular vision, stereoscopic vision. That's important because we come from animals that climb trees. Primates are tree climbers. And if you don't have stereoscopic vision and you reach for a branch and you miss the branch, then it's good night, Irene. So that's why we have that. You know who else has it are birds, raptors, hawks, owls, eagles, those kind of things. Because when you come down and you want to hit a prey, you better be sure you're going to hit the prey as opposed to hitting a wall. So they have to have stereoscopic vision too. So rotation of the orbits, yeah. I just use a dog here because it's just kind of your classic mammalian skull. Curiously, because the eyes in a dog do not face directly forward, they don't have a wall back here. We have a post-orbital wall. So if you point on the side of your head, you can't hit your eyeball. In a dog, you can. If you poke here, you'll see the dog's eye bouncing around. But we can't do it because we have a post-orbital wall. And the dog, his eye, he doesn't have stereoscopic vision, or at least not particularly good vision like that. His depth perception not very good, and his eyes point somewhat to the side. And if you think about it, horses and cows, any animal that's being preyed upon, then it always has its eyes pointed off to the side because it gives them 180 degrees vision all around. And the reason they have that, they don't have stereoscopic vision, but the reason they have that is because they're afraid something's going to sneak up and eat them. So that's why they have that. But primates have moved our eyes forward. That just shows you how the axis of the dog skull. And that's the same thing. And they have a great big nose, a big rostrum, a big snout. And inside of the snout they have all that nasal concha, all these things, which if you ever look at a dog's skull, it's filled with this stuff. And the reason it's filled with that is because that increases surface area enormously. And because you're warm-blooded, every breath, every time you exhale, you're pushing out fluid. Now, that means you'll dehydrate in a big hurry. So in order to stop you from dehydrating, you put these nasal concha in there that causes condensation in there, and that's why your dog has a wet nose. That's why most mammals have wet noses. We got rid of all that, and what's more, it's also for smelling, olfactory sense. We're not very good smellers because we've so reduced our face. And to top it all off, we cool off by sweating. Not a very good way to cool off, folks. But we can't pant. Our faces got so short, we can't pant. And you can try to pant, but you'll go acidotic and pass out. You can't do this for very long. But your dog can, but you can't, because we don't have enough dead space in our neck. You might just try that when you're alone at home. Okay, our orbits point forward, and on top of that, you know, see that little guy, what's that called? It's a cribriform plate. And the cribriform plate is where the first cranial nerve, which is the olfactory, comes up from the nose, and goes through the cribriform plate. Now this will, I'm gonna show you something a little later on. Now that little place right there, that's called sella turcica, which means turkey saddle. I don't know what a turkey saddle looks like, but I guess it looks like that. What sits in there? The pituitary gland, exactly. And right in front of that are these little holes for major nerves. What are those nerves? The optic nerves. And they cross right there. So that is the anterior fossa, that's the middle cranial fossa, and that's the posterior cranial fossa back here. These would be the temporal lobes, that's the occipital lobe, and the visual lobe, and these are, that's the frontal lobe. And, you know, so we've reduced the distance between our eyes, interorbital space, yeah. Now, here are the nerves. And what I want you to see here is that the occipital, the optic nerve crosses right in front of the pituitary. This is clinically very important because if you have a pituitary tumor, which God I hope you don't ever get, one of the things that you're going to know is you'll start losing peripheral vision because you're pushing on those nerves. And it's a terrible thing to try to fix. They have to go through the nose to get to your pituitary gland because it's way too deep to go in from the top. So they have to go through the nose, and it's just a very difficult surgery. And although this does not show it, there's a circle of Willis. Do you know what that is? Okay, at the base of the brain, you have all these arteries coming into your brain. And there's a little circle where they all come together. It's called the circle of Willis, and it kind of circles that whole brain stem area. And when they do that pituitary surgery through your nose, they have to be very careful that they don't hit that circle of Willis. I one time asked a neurosurgeon, I said, well, what happens if you hit it? And he said, as only a neurosurgeon could say, they die. You know what? Yeah, they die. Like, oh, well, let's stay away from that. So there's the optic chiasm. Chiasm just means cross, and that's where we cross. And the reason we cross is that gives us that stereoscopic vision. Here's your retina. And half of your retina, if you look on the medial side of your left eye, that retina is looking in that direction. Go to your right eye, and it's the lateral side of your right eye that's looking in that direction. So we take the same nerves, we separate them, we cross them at the optic chiasm, and then they come around to the back, to your visual lobe, and that's what gives you stereoscopic vision. And they cross right in front of that sella turcica, right in front of the pituitary gland. Same thing. Yeah, we've reduced our snout. All mammals, because mammals are warm-blooded, they have a real problem with dehydration. And humans have a terrible problem with dehydration. Now, I'm not going to, if some of you are long-distance runners, fine, I don't care. But you better drink. You better drink a lot of water. Because we're not made for long-distance running. I know, every now and again somebody's out there, well, running, that's what we're meant to do. No, we're not. We're meant to walk. We're the world's best walkers. But the minute you start running, it takes so much more energy, and it's so hard on your joints, and you dehydrate constantly, which is why in marathons, there's always those nice little ladies that are giving people cups of stuff as they go by, Gatorade or something, because you'll die if you don't get enough fluid. And every year, we hear about some high school footballer that dies. Well, what? Because his coach pushed him a little too hard. What kills you? I know you're going to say heat stroke. Well, what's heat stroke? What is it? I mean, you get too hot. I got that. I mean, I got it. What happens is, in order to cool off, you sweat. And you lose all your electrolytes, and you lose all your water volume. And eventually, your blood becomes so viscous that your heart can't push it anymore, and you die of heart failure. Your heart just says, sorry, I can't push this stuff. It's like Jell-O. Can't. That's why if you ever do exercising, drink water. Humans require vast amounts of water. Now this is neat. I have no explanation for this, but it's kind of a very, it holds across all mammals, at least the ones I've looked at. That is this. Your nostrils point down. Which direction do your dog or your cat's nostrils point? Forward. All mammals have nostrils that point forward. Ours point down. Now, that means we reduced our face, we got that. And there is the axis running through the nasal region. There is the cribriform plate. In other mammals, the cribriform plate is vertical. It's essentially perpendicular to the long axis of your nose. Not so in humans. This is really cool. We have twisted our face underneath, and now our cribriform plate is horizontal, and meaning that our nose, the axis to our nasal, is perpendicular once again. So as you tuck your nose in underneath your brain, your cribriform plate rotates from being vertical to being horizontal. Now, I don't know if there's a mechanical reason for that or not, but it is kind of cool. Now, did Hans talk to you about this? Okay. The whole nasomaxillary complex, that's essentially your face, your lower face, everything under your eyes. And this just shows that it is perpendicular to that cribriform plate. Now, part of the reason is your brain is going anteriorly out to this direction. Your face is going the opposite direction. So maybe it's just that mechanical thing that your brain is growing and your cribriform plate rotates because of that. I don't know. And there's your midfacial, but it's just, you know. The plane is from, is he talked about landmarks? Okay, anyway, this is just the front of your brain, the front of your frontal lobe, and then you draw a line through procyon, and procyon is right between, it's the space between your central incisors, and that defines your facial. The other one that's perpendicular to that is running through cribriform plate. And that just shows that we've taken our face and tucked it in under our skulls. Interesting idea. These are a couple more landmarks. Nasion is that space right between your nasal bones, top of your nose. Sella is sella turcica, it's inside that pituitary fossa. And then basion is the back of your foramen magnum. And that's how you measure flexion in the skull. So humans have a very tightly flexed skull. And that's just showing you the same idea. This is the posterior maxillary plane runs between the anterior and the middle cranial fossa, and it runs down to the maxillary tubercle. Do you know what the maxillary tubercle is? That bump behind your last molar? Okay, that just defines that posterior maxillary plane. In the midfacial plane, once you define that maxillary plane, then the other one is just the face. Why do I have a bulldog in here? We did terrible things. I mean, the only animal that suffers from sleep apnea other than humans are things like bulldogs. But remember, that's not a normal animal. We've so fouled up its genetics. Did I tell you why we did that? Do you know why a bulldog has a face like that? Well, there used to be something called bull baiting. And what they would do, they would take a bull and they would put him in a circle and they would chain him. They would chain him so he couldn't run and stake it to the ground so he couldn't run. And then they would take dogs and put dogs into that, and then people would bet on who would win, the dogs or the bull, to kill each other. I mean, I'm really glad that humans have changed. I mean, this is not that long ago, folks. They were doing this in the 15 and 1600s. Well, they developed the bulldog because the bulldog can bite and hold on, and it can still breathe. Most dogs, when they bite, they can't hold on. Like a wolf, it bites and it can't hold on because its nose, it can't breathe. It's up against the flesh. But a bulldog, they recessed its face so it could still breathe. That's why they're bulldogs. Isn't that, well, they also have a weird mutation that when a bulldog bites, it can hold on, it won't let go. Most dogs, when they bite you, just go choo, 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 choo. But a bulldog bites you, you're in trouble because it's not going to let go. And not just that, but also pit bulls, they got the same problem. They were meant to fight dogs. What's with humans anyway? This is just to show that we don't have much in our nose. We got rid of all the nasal concha. We don't smell. We can't smell very well at all. Interesting idea, though, that we can't smell because we have all the genes that would allow us to smell, but we don't turn them on. We don't turn them on. That's weird. But that's also why there are people that have an exquisite sense of smell. Some of you guys may have this. And they end up being chefs because they can smell in their taste, because smells, olfaction is tied in with taste. But also people that like make perfume and stuff. They have this incredible sense of smell because they turned on a couple of those genes that most of us didn't turn on. Now I could go on and talk about this a little later, but I'm not going to. It's an interesting thing here. This is biology, folks. It's just biology. Humans have something called hidden ovulation, or sequestered ovulation. I don't know if you guys are ovulating. I have no idea. I know you're thinking to yourself, well, thank God for that. Well, but do you know when your cat or your dog is ovulating? Oh my God, everyone in the neighborhood knows. And if you go look at a chimpanzee in a zoo, do you know when the female chimps are ovulating? Yeah, they get that big red thing around their butt, which apparently the male chimps find attractive. Doesn't work for me. But anyway, we can't smell. Your dog knows when you're ovulating. True. It doesn't tell you, doesn't tell us, doesn't tell anybody. But at any rate, in evolution, it's all about having children, right? How many offspring you have. The winners have the most kids. So why do humans have hidden ovulation? It's a curious fact. Other mammals don't do that. They advertise it. Humans don't. I could tell you more about that, but that would be a different class. It's probably why we can't smell, incidentally. That the males have lost our ability to smell. All right, bipedalia, we walk upright. What a weird way to get around. We think it's normal. It's not normal. You know, the fastest guy on the planet Earth, Usain Bolt, which I think, what a wonderful name, Bolt. If you're a fast runner, I mean, that is cool. You couldn't make that up. But Usain Bolt, when he hits the 75-meter point, he is decelerating. He can't keep that up. When he crosses the 100 meters, he's already decelerating. Now, the fastest guy on the fastest human on the planet Earth, can he catch a rabbit? Not even close. Can he catch a dog? No. Can he catch a squirrel? No. So we're phenomenally slow runners. And the reason we do it is for other reasons, but it's an interesting idea that humans are just, it's a bad way to get around. In order to do, we had to change our spines. What I want you to remember is this, right there. It's your cervical vertebra, right? Your cervical region. You've got a cervical region in your neck, a thoracic region in your chest, and a lumbar region in your lower back. You have a lumbar lordosis, what's called a thoracic kyphosis, where it reverses curve, and then a cervical lordosis to allow you to hold your head up. How many cervical vertebrae do humans have? 7. Every mammal has 7. So very, very conserved number. Every mammal has 7 cervical vertebrae except 2.
Giraffe.
No, but that's a good guess. Giraffe have 7s, but they're this tall. But they only have 7. A sloth. A sloth has 8. And get this, a manatee, you know, a sea cow?
Yeah.
A manatee has only 6. Those are the only 2 mammals that don't have 7 cervical vertebrae. You want to take a guess at why it's so conserved? Well, I know you guys don't work this far south, I know. But if you break your neck above C5, up here, you're in deep trouble. Well, if you break your neck, you're in trouble anyway. Let's face it, it's not going well for you. But if you break it above C5, what happens? The phrenic nerve, you paralyze the phrenic nerve and you can't breathe because that innervates your diaphragm. So, and the diaphragm comes from the neck, embryologically. It works its way down, migrates down into your rib cage. So that's the cervical lordosis. At the same time, to balance our head, we also move the foramen magnum forward. So our skull, although it's not perfectly balanced, it's balanced on top. Because if you didn't do that, if you kept it the way it is in a dog or other animals, you'd have to use your neck, your nuchal muscles to hold your head up all the time. Well, you wouldn't want to do that. Although when you study too much, you don't know this, you can get neck pain. You know, you fatigue your nuchal muscles and it starts to hurt. And when somebody falls asleep in class, they do this. Which tells you that our head's not that balanced. It's pretty close to balanced, but not quite. Yeah, we got a big brain. Everybody loves the brain. We'll talk about the brain in another couple of classes, why it looks the way it does, how it gets to look like that. It's a curious organ. And I will tell you this. That piece of tissue is 2 to 3% of your body weight, but it requires 25 to 30% of the energy that you consume. When you're a baby, it's 50% of the energy that you consume. So the brain is really something that is incredibly expensive from an energetic standpoint. And that just shows you that we have much bigger brains. And your brain tops out at about age 6 or 7 in its mass. Because the problem is you can't get the brain, it's got too big, you can't get it through the pelvis, which is why humans have a terrible time with obstetrics. Can't get it through the pelvis, so you have to get it out as fast as you can. It's still hard, it's still rough. You want to get it out there, but look at that growth trajectory. After birth, that thing is just multiplying like crazy. It's not neurons though, it's all glia, which is the hacking material. But at any rate, humans have a huge brain. We had to change the way we even grow the thing because we couldn't get it through the birth canal. And what happened? Well, we expanded our frontal lobes, we expanded our temporal lobes out over the face. And that just, you know, once again, know your cranial fossa. You know, these are the anterior, the middle, and the posterior cranial fossa. The cerebellum sits back here. Temporal lobes sit in that fossa, and up here the frontal lobes. So we grew the brain out over our face and at the same time tucked our face in. Now this is an interesting thing, we'll get to it. Yeah. Now we not only tucked our face in, but we moved the foramen magnum forward, which means our postlaryngeal space is almost not there. And that's why we suffer from things like sleep apnea. We've got no room back there. Why we tucked our face in so tight is a really good question. Why did we have to reduce our teeth? So through evolution, you see the face getting more vertical and more vertical. And our palate, this is the human over here, we have what's called a parabolic shape to our palate. And that parabolic shape, in order to achieve it, we had to reduce the size of the canines. This is a chimp, look at the size of the canines. This is one of our ancestors from about 3.5 million, still has reduced canines, but still large. Humans have no diastema, no natural, and a diastema is a space between the teeth. If you go home, look at your dog or your cat, there are spaces between their teeth, between the incisors and the canine and the premolars. And the reason they have a space is so when they close their mouth, there's room for the canine to fit. They're big expanded canines. Well, we reduced our canines and we don't have any diastema. If you look at a chimp, that's a diastema right there. And that just shows that we've, shortened our face. And doing so, what we have done is we've reduced that post-pharyngeal space to the point where, look at this, here's our trachea, there's our esophagus. Now, number one, if you were building the body from scratch, you wouldn't put the trachea in front of the esophagus. That was stupid. But we had to do it because evolutionarily, that's the way it is, looking at fish. And when you pulled it all down, that's why we did that. Well, we have to have an epiglottis, that little guy right there, that when you swallow, it closes off your trachea so that you don't choke every time you swallow. This is a major issue because humans choke to death all the time because we have no space. And when you get older and the muscles that control the epiglottis become compromised because of age, then what happens is you start to aspirate food and liquid. And that's why you die of pneumonia. You aspirate that into your lungs and that is what kills you. Other animals don't have this problem. And we reduced, we've talked about this, we've actually gone so far that we're getting rid of the third molar. We almost got rid of it. Because now, if it does come in, it's impacted, it causes all kinds of problems. If you go into orthodontics, it's a major issue because, you go to all this trouble of fixing the teeth and then the third molar comes in and screws it all up. So what do? You take them out. So now, does anybody here have their third molars? You do? All 4 of them?
Yeah.
No kidding. Do you have yours?
Yeah.
All 4?
Yeah.
Good for you. I don't. They took mine out. Mine are gone. I mean, who's had surgery? Which is a brutal surgery. I gotta tell you, I ruined so many harmonicas with this one. It's a long story. I play blues harmonica. I ruined all my harmonicas because of the blood. It was awful.
Oh, Christ.
I know. Don't talk about it. It makes me sick too. Not to mention the fact that I lost all my best harps. So that just shows we have impacted. We are almost losing them. And this is kind of fun. This just shows you of the different cultures and different groups around the world who was losing their third molars fastest. The Asians, which is why I'm surprised you still have all your 4. That's just because Asians have an orthognathic face, a flatter face, right? So you have less room than we have. And the blacks, they have a longer face, a prognathic face, and they have more room, and so they weren't losing their third molars nearly as fast. So in an evolutionary sense, the Asians are ahead of us. Okay, you guys, I'll give you that. But it is kind of neat that we were well on our way to losing them until culture stepped in, and that's you guys. And in the same process, we reduced the size of our teeth. This is just simple measurements, mesodistal and lingual buccal and the surface area. And humans are way down here. These are some of our ancestors. And our teeth have gotten smaller, 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 smaller. And the reason is because as your face is shrinking, you end up with malocclusion. And humans are the only animals that, if you will, naturally get malocclusion. In domestic animals because of what we did to it. But and that's how you can tell a domesticated animal from a wild animal, is that wild animals don't have malocclusion. If you look at a domesticated animal, it's very common. Humans almost always have some sort of malocclusion, except for the Inuits, the Eskimos. They had perfect teeth because they would chew on leather and do all this kind of stuff. They had really, really good teeth until we gave them Twinkies and Coke and Pepsi and Ho-Hos. And now they're just as bad as we are. Too bad, too bad. Take home message. Don't tell people I said this because I don't want social services calling me up. But if you wanted a child to have nice teeth and a nice mandible and nice maxilla without crowding, give them rawhide bones to chew on. There's a reason puppies chew all day long, because they chew on their shoes and stuff. Well, there's a reason that they do that, because that helps the teeth come in and grows the mandible to the right size. Because your teeth are genetically programmed, but your mandible is not. It's wool slaw. Remember, if you don't stress it enough, you've done wool slaw, right? Okay, it hypertrophies, bone hypertrophies under stress, it atrophies in the absence of stress. So if you don't stress it enough, it doesn't reach its potential, and that's why you have malocclusion. And the teeth, if you even look at the teeth, the third molars in humans are malformed. They don't look right. And if you look at the second molar, we're supposed to have 5 cusps. Well, we don't anymore. We only have 4 cusps. If you go back 100,000 years, we had 5 cusps. So we're losing a cusp on that tooth too. All right, now, here comes the fun part. 300,000 years ago, Homo sapiens developed in Africa, in East Africa. That's us. That's not very long. I know you're thinking to yourself, my gosh, 300,000, that's nothing in an evolutionary sense. There's only one mammal that's younger than we are. Do you know who it is?
Polar bear.
Polar bears, yeah, the polar bear. Too bad, because now with climate change, polar bears aren't going to be around much longer. But anyway, so then we left Africa and we went all over. These are both Homo sapiens, but this guy does not look like this guy. This guy has huge brow ridges. He has a brain the same size as yours and mine. He's got a great big face. And this guy, look, he has no brow ridges. His face is wimpy. I mean, there's not much, that's kind of a weird skull. Now, one of the reasons is, it's called pedomorphism, which is that you maintain a adolescent or a sub-adult face. This is a baby chimp, that's an adult chimp. So obviously, in order to grow that big face, a huge amount of growth had to occur there. And one idea is that humans maintain that face that a baby chimp has. Well, here is a modern human like us. Here is what's called a Neanderthal. And they were running around with us up until 40,000 years ago. At 40,000, all the Neanderthals went away. We don't know what killed them. I got a pretty good idea, but we don't know. But look at the difference in those skulls. Now these are so close to each other that they could mate. I'm sure you all know this. If you are white and come from Europe, you have Neanderthal genes. You have them. We only figured this out like 8 years ago, when they finally cracked the genome of the Neanderthals. Major breakthrough. So you've got somewhere around 2, 3, 4% of your genes are Neanderthal genes. Asians, you're not getting away. You have something called Denisovans, which is another group like the Neanderthals. And you guys carry those. If you're black, you know what? You're purebred. You don't have that stuff. That's what my friend that works in the Natural History Museum, Haile Selassie, is. Yeah, I'm a purebred. You mongrels, I don't know about you. Which he's right. He's right. But look at the difference between this and that. I mean, it's a huge difference. they have that sloping forehead, they have giant brow ridges, they have a huge face, they have something back here called an occipital bun. The skull is what is a very long skull, which would be dolichocranic. Did Hans tell you about that? Okay. And we have a brachiocephalic skull. They have a dolichocranic skull. Some people still have that long skull. And you know what? Those are the genes. They also code for the shape of the brain. Now, there's a Neanderthal, there's a human. We have a model. There's a wolf, there's a dog. What's the difference between the wolf and the dog? Smaller face, smaller teeth, smaller brain, smaller everything. Smaller mandible, smaller maxilla, just like the Neanderthals, which are wild humans, versus us. So what's going on? Well, it's this. My favorite thing, neural crest cells. Remember neural crest cells? I know you're going, oh God, please don't make us do that again. Oh, come on, man. Neural crest cells migrate around the body. They delaminate, right, from the neural tube, and they migrate around the body, and they form melanocytes, which is skin pigmentation, actually not just skin, pigmentation all over the body. They make chondrocytes, which is cartilage. They make osteoblasts, not osteoclasts though, osteoblasts. They also make essentially your sympathetic nervous system and your parasympathetic nervous system. So they do all this stuff. The important thing is that when you domesticate an animal, you don't want that animal to bite you. So when you domesticate it, you're selecting for tameness. And when you select for tameness, what you're actually doing is cutting back on the epinephrine, adrenaline. You don't want them to bite you. You don't want that fear response. So you're selecting to reduce the size of the adrenal gland, actually the medulla of the adrenal gland. And that reduces the amount of epinephrine. So it becomes tamer. And that is controlled by neural crest. So in selecting for tameness, all this other stuff came along for the ride. There was nobody ever said, I want a dog to have a smaller face. That's not what they were after. Not at this stage. Or a horse to have a smaller face. Or why your cat has white feet. Because the melanocytes never got down there. And why dogs and horses have a blaze on their forehead, it's white, because the melanocytes never got there. That's not normal. So all that was never selected for. It just came along for the ride. All right, I'm not gonna. We'll talk about this later when we. But you know, you've got the neural plate, and the neural plate, starts to fold in upon itself, and it forms a neural tube. Here's the notochord down there. Forms a neural tube, and at the top of the neural tube, you get these things that are neural crest cells, and they delaminate, which is important because it means they turn into mesenchyme. Remember ectomesenchyme, and they can migrate around the body. And they go all over the place. It's just vertebrates that do this. Invertebrates don't have neural crest cells. This is a major breakthrough. And what did they do? Well, they do all this. The important thing is that they reduce the adrenals and the medulla, and that means that the sympathetic ganglia, you're reducing stress, the whole fight and flight response. And along for it comes differences in, floppy ears because of the cartilage. You also get white patches in the skin. You get all kinds of this stuff, but that was never selected for. It just came along. Remember, your face is neural crest. So by reducing the amount of neural crest cells, that's probably why our face got shorter. Because we live in large groups, and you have to, when you start living in a larger group, you have to reduce male aggression. Now, yes, we're still killing each other, doing terrible things, but we don't do it the way chimpanzees do it. They're terrible animals. We've so reduced our aggression down so we can live in larger groups. But the point here is, this is what was selected for, was tameness, the change in the face, and the change, this is strange, in the size of the brain gets smaller. And for 100,000 years, the human brain has been getting smaller. Neanderthals have bigger brains than we have. Now, I'm not saying we're stupid. That's not true. We're not. But we are reducing the size of our brain. I'm not even gonna, you know, I just, when I show that things like this, I can just see your faces going, oh no, please, not that. Just remember, neurocrest, all those bones in your skull are neurocrest with a few areas like the occipital area and like the mandibular condyle are not. But everything else is basically neurocrest and membranous bone. Remember membranous versus endochondral bone? Now, I only throw this up because you are going to have to deal with some of these systems. When the neural crests do not go, what's called a neurocrestopathy, they do not go where they should go, where not enough of them get there, you have all kinds of issues. You have problems in the face, terrible problems in the face, problems in the teeth. Why? Because dentin is created by neural crest. And it turns out probably enamel is too, but like that, because that's still under investigation. But certainly dentin is. So all of these things are being reduced. Now, you change the shape of your skull because of neural crest. You change the shape of your ear because of the chondrocytes, the size of the cartilage. So people that have neurocrestopathies very often have odd-shaped ears. You change the shape of your mandible. It becomes smaller, and your teeth get more crowded. You even reduce growth. So all of these, and the adrenal gland changes. So all of these things fit in together, along with, in their, what's called a neurocrestopathy, and it has behavioral problems. It has things, your bones are different, your skin is different. All of these things come about because of changes in the neural crest. So, here's the human, that's the viscerocranian. Just remember, when you reduce the amount of neural crest cells that are migrating out of the neural tube, you reduce the amount of tissue that they produce, and that's probably why the humans have a reduced face. It's probably why we have smaller teeth. And even now, we still can't even fit all of our teeth in, and that's why we were losing our third molar. So it all really does go back to neural crest. So, nobody in this room looks like that. Good thing, too. And my guess is, this is what a wild human would look like. And it's also my guess that if you ever bumped into one of these guys, without hesitation, they would kill you. So I think all of that, so the behavioral changes, the anatomical changes, the physiological changes, are all a consequence of that we self-domesticated ourselves. And that's why we look like we do today. And that's the end. I think, yeah. So, study your neural crest. Next time we'll do facial stuff. Just remember your